evening, everybody, and welcome you to the very first Reatch pitch. Very happy that so many of you found their way up here. I hope nobody got lost in the building. I think from what people told me, it's not as easy to find as other rooms we have held our events in so far. What is a Reatch pitch? Reatch pitch is a new event format that we established as Reatch, in which we want to present you controversial, interesting, or little-known facts from the world of science and technology in a short and concise manner from experts, but also in a way that a general audience is able to understand and to follow it. Today we start with quantum computing. I'm very happy to present Bettina Heim. She's doing her master's at ETH Zurich in the working group of Matthias Streuer. And she recently published a paper in Science about quantum annealing. If you don't know what it is, don't worry, she's going to explain it. And if you still don't know what it is, there's plenty of time for you to ask questions in the end, or also during the event. And now I want to give the floor to Bettina. Thank you very much.
So hi everybody. I'm glad you could all make it here, and I've got the full responsibility to make a good Reatch pitch as it's our first. The topic is certainly very interesting we have today. It's all about quantum computing. There's this one magical word, quantum. Every dishwasher recently promises to use something quantum to make your dishes clean. But of course quantum computing is even more interesting than your dishwasher. So, you've probably all heard articles in journal about safety, about quantum algorithm that should make a computer 1,000,000 times faster. We're gonna do a nice introduction today. So, because I'm a theorist, I could now pull up the blackboard and, yeah, already. Yeah, I'm a theorist. And do something like this. And you would be all very happy and probably understand absolutely nothing of it. So I'd rather not do that. I try to avoid all formulas. It's all very simple. And please feel free to just shout if you don't understand something. I'll try to explain. Though actually the major part of my talk is not really about the things I work on, but more of a general introduction. So I hope you're a bit patient with me if I don't know every experimental question you may ask. Okay, if I can answer, I'll answer. If I feel I cannot responsibly say anything about it, I'll just say so, if that works for you. So as I said, we'll start with the basics today. We go back in time, way back. And when you hear the word computer, you should first ask yourself, what do you expect of a computer? If you say we want a quantum computer, everybody of you has this picture in his head of what a computer actually is and what it's supposed to do. So let's go way back to 100 BC, actually, when there was one of the first, or at least one of the found analog computer, and it worked mechanically, pretty much like a watch. It had a lot of mechanical pieces, and they were designed to predict certain astronomical events. And it was actually used for the Olympics Games, I read. So by now, we've gone a bit farther in time, and around 1950, there it was actually something similar like a computer, I'd say. It was still 500 kilograms, half a ton. It could save 90 numbers. So it was a very, very heavy pocket calculator, essentially, just much slower, because it needed like 5 to 10 seconds to actually multiply something. So it was a really huge pocket calculator. But incredibly, not even 20 years later, sorry, wrong date. I keep finding mistakes. There's already something that we would recognize as a computer, probably. Apple I. It didn't yet come with actually a screen and a keyboard like you're used to, but it was designed to be able to work with a keyboard and a screen. So you could buy it yourself, plug it together, and do some programming and calculations. That was really nice. It even had an operating system. So it's starting to get higher and higher level. So now that we've looked a bit at these computers, I'm not going to go until today. You all know what you've got today. You all work with it. You should ask yourself, well, what is a computer actually? And what do I expect of a computer? So let's maybe ask the dictionary what a computer is. And the dictionary tells me it's a programmable electronic device designed to accept data, perform prescribed mathematical and logical operations at high speed, and display the results. So we want something programmable. It should take some input. It should do something with it, and hopefully what we wanted to do with it, not something else. And it should give us some results that we can do with it. Okay? So this is summed up here. So when I start and tell you we're going to talk about quantum computer, every one of you probably expects something like this. Okay? Something very similar. It should take an input, it should give an output, it should do something with the input, and hopefully 1,000 times faster than my computer at home. Okay? So let's quickly look at the definition for a quantum computer. And here the Smart Dictionary is already much, much shorter. It just says, well, it's something that makes use of quantum states of some particles or others to process information. So basically, it's just supposed to work in some quantum way. Now, we could ask of it that it still takes input, that it stores this input somehow, and it stores it sufficiently long to actually perform calculations, that it can do calculations on the input, that we can tell it what it should do with the input, and that we actually get something out. But these are already quite a lot of requirements, and they're not just satisfied like that. Each one of these has to be implemented very carefully if we want to design a new type of machine. Some of them are easier, some of them are harder, and maybe we need to drop some of these to get something that's working. Okay? So we want to make it quantum. All right, so probably we still would like to have a classical input and output, just because actually we as human beings cannot really read quantum. Nobody of you knows how a quantum state looks like. You just know the classical version of it. So to know what we are actually feeding it and what we are actually getting out, in the end, it has to be classical. But then we want the quantum computer, so somewhere along the way it should probably do something quantum. So it should actually probably perform operations that at one point or another, this input becomes quantum. So let's say the input should be stored in some quantum form, and the operations should use some quantum effects. Okay? That's the thing we work with so far. Now let's look at a model of this machine. This is the classical thing. We have some input. This goes into our computer. We don't know yet what it does or how it works. But we know something comes out, and it's what we want, hopefully. We can make it a bit simpler, and for now just consider one input getting one output. Okay, it can be 0, or of course it can also be 1. But the important part here is that it can be either 1 or 0 that goes in, and either 1 or 0 that goes out, but not both. That's classical. So now let's look at the quantum version of it. You all heard of the famous Schrödinger's cat? I assume. Okay, great, Schrödinger's cat. I don't need to explain it. So let's take Schrödinger's cat then here. Okay. Now we have Schrödinger's cat going in. It's halfway dead and halfway alive. The computer does something with it, and out comes a cat that is more or less dead or alive. Nobody knows exactly. But then, of course, this is not quite true, because as I said, your Schrödinger's cat that you have this experiment, you set it up, you put her in a box, You close the box, have some poison in there, then you're not quite sure whether the poison has already come out and it's died or not. But before you can have that cat in the box, you actually have a cat, and you need to put the cat in the box. So at the beginning of this whole story, the cat is very much alive. Then you put it in a box, let it there for a while, so you're not quite sure anymore whether it's still alive or not. Then our quantum computer makes some calculations. Hopefully does something that our cat is rather more alive, because I like cats. Then you can take your cat out again. This is just measurement symbol. That means just you open the box, look in, see your cat is still alive, and hallelujah, you got your cat back. Bit boring, the computation, but still quite interesting. So this is a principle of a quantum computer. And you've already learned the most complicated concept of quantum mechanics everybody always makes fun of. Well, you're never quite sure whether you're here or there or whatever. Okay? So let's go on and look what we can do with this. So what's the difference between quantum computing and classical computing? Well, the first thing is a computer has bits, the zeros and ones, and a quantum computer has Schrödinger's cats. They're 0 or 1 or maybe something else. Probably most of you have also already seen this sphere like this to represent the quantum state. Who has seen it? Yeah, okay, so not everybody. It's just a way. Okay, I wasn't sure who would come. Okay, so basically, classically, you have only two possible points that you can give into your computer, either a 0 or a 1. Quantum mechanically, you can give all these points here. Well, let's maybe just talk about the surface, but principally also all points inside this sphere, and it will do something with it. Okay? Outside on the surface of the sphere are pure states, inside are the mixed states. For everybody who's interested, the rest can ignore it. Okay, yeah?
Yeah, just a question. Why would it be three-dimensional? Because between a 0 and 1
it is quite, well, it's just a mapping, you see. I mean, you have you had like mathematics something? Ah, no, sorry. Yeah, you have to look at groups and isomorphisms if you want to understand. It's just mathematical, it's a mapping. You can map all possible states onto a sphere. I mean, it's not a sphere, but it's isomorph, so we'll take the sphere. It's nice to watch. Okay? So that's one thing. So let's look if we can already do something with our qubit. I took a quite the easy example out for you. That's really just an example. It has, as far as I know, no application, but please correct me if I'm wrong. But it's nice to illustrate, and it was the example of why people became curious about quantum computing. So our task is, we have a function. It maps 0 and 1 onto 0 and 1, just the way I drew the picture before. We're now supposed to find out whether both 0 and 1 are mapped to the same, to 0 or 1, or whether they are mapped to something different. Okay? So classically, well, there's not much to do except just try out both inputs, see if we can get the same, and yeah, then we have our answer. This, however, needs two function calls. Now this f, this function, this may be really ugly. It does something very trivial, so by just 0, 1 to 0, 1, but it may be really ugly, it may be unknown, it may be very expensive to calculate, or whatever happened to it. So two function calls may be quite expensive. It would be better if we could get just one function call. So let's see what we can do quantum mechanically. Quantum mechanically, we need something like this box here. And we basically just assume that we have this box. What this box does is it takes an input, or it takes two inputs rather. It does something with these inputs so that it gives out the first input again. And as a second output, it gives out the second input and addition modulo 2, that's just this strange symbol, with the function of the first input. Okay? So I think you can agree that's one function call. All right? Now let's feed this box. We can feed it with these states. That's basically my Schrödinger's cat, and the Schrödinger's cat 1 times upside down or something. I don't know, but pretty much that. And we can do a measurement on our outputs and see what comes out. We do a measurement with respect to these 2 states, these are spaces. I left out a few gates to make it a bit simpler, so I'll just directly describe these as inputs. The point is that if we measure the first output qubit again, we can say with certainty, in fact, which case we have, if this is true or not. That's quite impressive. So we just have one function call. So classically we need 2, quantum mechanically we need 1, and yay, quantum mechanically it's better. Now before we start to look at what we can do with that, I would like to quickly say something about this box here. And it's pretty much what's called an oracle. And an oracle is just some kind of subroutine. It's quite practical to describe algorithms in abstracts if we don't know exactly how this box will look in reality. So you can actually, as a theorist, say in principle that and that works better. Now you need to realize it. Now you need to build it. But this box still needs to be built. And that may not be easy. That may not be straightforward. Or actually implementing this box may also be very expensive. So that's something you should maybe keep in mind when we discuss some other algorithms. I'm not going into too much detail there. But there are a lot of quantum algorithms that actually use an oracle in one form or another. That oracle is always assumed to have constant costs. So even if you have a bigger system, you shouldn't have more effort to perform the oracle call. And what's important, what you have to take care of, is that there are no stray qubits resulting from the call of the subroutine. Because if you have any, that may give interference with the qubits you have, pretty much what we actually used to our advantage previously. But if we just have anything, it may not be so good to have that. Yeah?
Just a question. I don't get where do you know from what the function of y is in this box?
Function of y? You mean?
Isn't it that you wanted to find out if the function of y is or the function of 0 is the same as
Okay.
function of 1?
Yeah, we did. I didn't write down all the math because it's just math. We can quickly look at it on paper afterwards if you want, or in a book. If you feed it with the 2 states that I wrote down here and perform exactly this operation, you'll see that you end up, I think the second qubit is in this state, in either case, no matter what the input is, and the first qubit is in fact, I think, in either this state or in that state, if I have it right in my head. And the point is, actually what you would do after that is still a Hadamard gate. So you map your Schrödinger's cat to dead or alive again, so to say, and then you end up with an expression for your first qubit that's just f of x plus modulo 2 f of y. And that's just math. I didn't write it down to make it understandable. But if you want to know, I'll show you. Yeah?
So is the output of this box, is that steady, or is it like fluctuating all the time, and you just, if you look at a certain time point, you will see that f of 0 is f of 1?
No, it's actually here, if you measure the first qubit after you've performed the operations, you get with certainty your answer. So that's a deterministic quantum algorithm, which is rather rare, I think. Because I always claim, like, by definition, it's more or less probabilistic, but this one actually works with certainty. But it's a constructed example specifically to show that quantum can help. Okay? So let's see if we can do a bit more, if you have more than just 2 qubits to do something with. And if you have a bit more qubits, there's this nice thing called the quantum Fourier transform. It's not an algorithm in itself, but it's a very useful tool, and a lot of algorithms that use it actually. So I'm sorry if anybody's hoping to get the quantum Fourier transform explained. It's quite boring. It's the same as a Fourier transform, just with quantum states. So I'm not going to explain it, but I'm going to quickly say what you can do with it. And one nice thing that you get from it is Shor's algorithm that most of you probably have heard too. The task is, given an integer m, that is the product of 2 primes, let's assume for now they are the primes, we're supposed to find p and q. Or 1 will do, as there's only 2 making up m. So classically, that's really hard. Do you know what it's used for, classically? Yeah. Yeah, exactly. So it's so hard, you actually encrypt your data using just this principle. Okay, so basically your public key is m, and then you got your private key with q or p, and that's how it works. So it turns out that quantum mechanically, this problem is solvable in polynomial time. So that's an exponential speedup. That's huge. That's bad. Okay, our encryption is gone. And that's why quantum computers are really interesting. So, yeah, just to give you some numbers, I haven't calculated them myself, but I think they should probably be okay, because exponentially bad is really, really bad. Okay, so if you have like 1,000 bits, your classical computer will take some days to find out the solution to the problem. Your quantum computer will take some minutes. If you have 4,000 bits, if you take really long encryption, it gets worse, because a classical computer will just never break it. It's around 1,000 years. Whereas your quantum computer, well, go drink a coffee, have a nice dinner, and you're done. Okay? So exponentially is really a huge, huge difference. So does that mean we're kind of screwed? The first one who has the first quantum computer just reads everything. Well, that's what theoretical physicists are for, because they like their privacy too. And they're, of course, working on quantum encryption as well. So even though you could probably use this algorithm to actually decrypt some of the files as we send them now, if we manage to build a quantum computer that is so good as to implement that thing here, we will also be able to encrypt things reasonably, the quantum way. So I'm not going into that encryption just for the sake of time. So, but it's really interesting. Then what do we have? We have quantum search algorithms. That's also quite important. Probably you've heard Grover. Okay? So the problem is you have a function again. You have now a bit string, just a word on your computer, and you get a yes or no answer. Okay? So basically you ask a question and somebody answers yes or no. Okay? Now what we know about this function is that the answer is yes for exactly one input, one question, and all the other times the answer is no. The algorithm actually also works if there are several yes answers, but it's easier to prove with just one. So classically, if you don't know anything about this function f, you have no choice but to just ask every question that you want answered and see what you get. Sometimes you're lucky and you get your answer the first time, and sometimes you're not lucky and you get it the last time. So overall, you need probably n half tries or something. So that's of order n. Quantum mechanically, you can speed it up. So you just need root n questions of that size. Now this does not sound or look very spectacular with that function here. It looks like really boring. You're all wondering what to do with that. Let's see, maybe you could solve your Sudoku that way. You could ask, is then that the solution to my Sudoku? The answer is either yes or no. Okay, so if you have a quantum computer, you're really good at Sudoku. But you could also use it to search unsorted databases. Now again, this sounds kind of vague. I don't have an unsorted database at home lying somewhere. So I would say, yes, you do. It's the phone book, for example. In a phone book, it's very easy to look up by name. You just go through the ordered list. But if you want to look up a number in your phone book, it's really bad. Good luck finding that number in your phone book. And that's what an unsorted database is. And what you can do with that, in particular, is crack passwords too. Because your password is basically just, for me, I can ask you, is that your password? The answer is either yes or no. So it speeds up that process. So it is actually quite important. And the point is basically every problem you have can be formulated in the way with this function f. The other point is that sometimes it does not make sense to formulate it that way. Because here with that algorithm, it speeds it up, yes, but just quadratically. And if you actually know something about that function f, they just may be better ways to find a solution. Because f has certain properties. And you can use those properties. So basically every problem you can formulate so that you could use Grover, but not for every problem this makes sense. Okay? Good so far? We're almost done with algorithms. Then keep on going. So, one more important thing, entanglement, not this entanglement here. I thought you needed a cat by now. So, what do we mean by entanglement? Who knows what entanglement is? Oh, great, a few people know. Okay, great. So, this is entanglement. Okay? If you look at this, that just denotes the state of two qubits. So always the first number in these arrowy things denotes what the first of these qubits does, and the second one belongs to the second. So basically, that's a quantum state. You can never really observe the quantum state. As soon as you observe it, you'll either see that it's 0, 0 or 1, 1. And here entanglement means that if you measure just the first qubit of the twos, you immediately know in what state the second qubit is. Because if you see, oh, the first one is in 0, then you can conclude, yeah, the second one is in 0 too. If you see the first one is in 1, the second one must be in 1. And these two qubits, that's kind of the whole thing about it, they don't need to be together. They were, at some point, they were generated in a lab. They were from the same light source, for example. But then they were split. Maybe one qubit is by now in a solid, in an NV center somewhere, and the other qubit is 2. They're still entangled, but they're separated by miles. So that's one other funny thing about quantum mechanics, that if I observe one particle really far away, it actually changes the state of the other particle at the other end of the world. So quantum mechanics is really fun. You should try it. Okay, so what can we do with it? For example, quantum teleportation. Probably a lot of you have heard about that one too. And again, I'm not using formulas. I'm just saying what the task is and how we can solve it. So basically, we want to send a qubit from Alice to Bob. Every physicist loves Alice and Bob. If you ever have a boring story, just use Alice and Bob. Everybody will listen. So what can we do? One possibility is just to, well, send the qubit. Put it in the mail. Send it by post. It will arrive. Okay, but it might get destroyed on the way there. Okay? To do that, we need a quantum channel. A quantum channel is always noisy. By the time it arrives, it may just be lost or something. Okay? Then the other possibility is to teleport the qubit. Now, one important thing here is to know that there are no fax machines. There are no quantum fax machines. There's the so-called non-cloning theorem that states that you cannot perfectly reproduce a quantum state without destroying it. Yeah. So basically, if you want to send quantum information, we have quantum teleportation, you destroy Alice's qubit, and Bob afterwards has a qubit that is in exactly the state that Alice's qubit was previously. Okay. The way that works is that Alice and Bob share such an entangled pair of qubits, as I explained before. Okay, so at some point they were in the same lab, they had a nice friend, that friend produced some qubits and gave each one of them one half of this entangled pair. Then they split their ways, went abroad or whatever, and at some point Alice wants to send Bob the message, this quantum message. For that, she needs an additional qubit, and she performs projective measurements on her 2 qubits. Now what happens when she does that is that the entanglement from Alice's and Bob's qubit goes, in fact, to her 2 qubits. So the entanglement shifts its place, and Alice can afterwards just tell Bob what she measured. See, she needs a classical channel for that, so relativity still works, great. Okay, no fuss about that. And if Bob knows what she measured, because Alice's measurements actually changed the state of Bob's qubit, he can now apply certain transformations. So that means some gates, he shines light on it or something like that, to get exactly the state that Alice had. Again, without math, but that's the principle.
One question about this.
Yeah?
So you have the quantum entanglement in the first 2 qubits, and then she performs her experiments, and then the entanglement of her qubit goes over to the second qubit she's performing the experiment on, while maintaining the entanglement with the above qubit.
No entanglement, no more entanglement there. There's something like the monogamy of entanglement, meaning, yeah, it's nice. Quantum mechanics is nice, you know. So, yeah, so we cannot be entangled, or at least not maximally entangled with 2 qubits at the same time.
Mm-hmm.
If you're really committed, then it's just one.
Okay.
Yeah?
I don't understand, what's the use of changing the state if you can't control how it will change? I mean, she can send you information, but it's random.
What do you mean it's random?
Because, as I understand it, you measure it,
Mm-hmm.
then it takes one of 2 states. So you can't control which one it will take.
Yeah, okay, we kind of know that they had an entangled state at the beginning. So we know that based on her measurements, we know what happened to those states. And if you, again, write it down, you'll see what operation you need to apply to Bob's qubit to get exactly the state that Alice's qubit was. And I mean, so personally, I really like the formulas because it's really sometimes counterintuitive and everything. So it really helps to just calculate that through. It's just if you sit down, calculate it, you'll find that this actually works. And it's not clear why it should work. I mean, just, yeah?
Has this been like replicated in the lab?
Yeah, it has. There have been, I think, quite a while ago, 1990 maybe. Probably should know, but yeah.
And distance is not a factor in quantum teleportation, is it?
Well, I think it was replicated with photons. So you see photons, they're generally hard to detect. And I mean, at some point it becomes an issue, just, yeah, there's theory, that's really nice. And then there's reality, and the reality is just a bit messier. So, yeah. Okay. So what can we do with that? Well, quantum teleportation is used to implement gates, so a bit more practical here. And entanglement in general is used in quantum error correction. And again, I'll not tell you a lot about quantum error correction for the sake of time, but you should know that you need quantum error correction because there's noise. Even if the theory says, yes, your result is 99% reliable, the reality in a lab looks quite different. It's really hard to reproduce the theory in a lab. So you'll be glad for quantum error correction. In theory, there is quantum error correction, but I never tried to implement it. I was told by experimental physicists that it's quite hard to get it working, but I cannot judge that. Okay, so we have these nice algorithms, and just a quick overview of what you can actually do with quantum computing in general. So you have these quantum algorithms in one part, there's quantum cryptography, quantum error correction. Well, that's mostly if you actually want to perform quantum computations. A bit newer, there are some people interested in quantum machine learning, but it's still a work in progress. So number generation would be a nice thing, because you could assume that classically you probably cannot generate good random numbers, and if you don't really care about random numbers, then you've never really thought about them, because they're really essential in every experiment. You're really dependent on them. Okay, there are a few devices already that can be bought, but I think they're not spectacularly good. But in principle, again, you see a lot of theory. The hope is that it could work better than classical. So that's something to find out. The other 2 points that I'm going to tell you a bit more later are simulations of quantum systems, because if you ever try to simulate your quantum system on your laptop at home, it's really bad. Okay, don't try it. Seriously, it's frustrating. Okay, so that would be one application that doesn't sell very good, but is very important for every researcher there is. And these combinatorial optimization problems I'm going to introduce a bit later in 2 minutes. Because I promised you at the beginning that we would stay close to reality and start actually with our perception of a computer and everything. So I'd like to come back to our defined properties that we had. Yeah, so I've talked a bit about what could happen in this computer. This part about a classical input and preparing a suitable quantum state, these are separate parts where actually experimental physicists specifically work on being able to produce whatever quantum state they want. But I don't have much experience, so I'm going to leave that one out. And the operations that how you actually implement these operations depends hugely on how you store your qubits. So because there are currently a lot of different schemes how you could possibly store quantum information, I'm not going to go into depth about this part, and just quickly tell you what these qubits actually are. I mean, on an abstract level, they are just 2-level systems, which means they can be basically anything. So we're going to take a look at these 2 points. Qubits. What are qubits? I'm always talking about them, but I haven't told you yet what they actually are. So the easiest thing probably to imagine for you is just a ray of light. Like photons sound quantum, so they probably work as qubits quite well. And actually your qubit states are just polarizations. You could also take, however, the coherent states of light, and then your 2 qubit states are just the squeezed states with respect to amplitude and phase. Okay, not so important if you don't know what squeezed states are. It works with photons. Photons are really great because they don't really interact a lot with environment, so that's good. But then they are maybe hard to detect, and they get lost on experiments, so that's a downside for them. There are quite a lot of experiments with flux qubits, and maybe a bit less with charge qubits. This works with a Josephson junction for the physicists, or I don't know who knows about that. And flux qubits are probably, from what I see, the easiest thing to scale, to actually have a few and not just one. You could use electron or nuclear spins. So the spin thing, who knows what spins is? Yeah, the thing that goes up or down. That's exactly our 2-level system. So that's very straightforward. It's not so straightforward to actually manipulate the spin of an electron in the way you want it, and just of that electron and not everything around it. So it's a bit harder. You can also work with defects. in solids. The good thing about these is that they live quite long, so it would actually be something to maybe store a quantum state. Then there are quantum dots, which are also tested in hybrid systems with several techniques to process information, and ion traps, which also live, so the states in ion traps, I think, also live quite long. So that's nice. What are the problems? No. Now we have so many possibilities, so it should be easy to get some working qubits, right? Well, the problem is they are embedded in the environment, in air, in rays of light, of everything. They interact with an environment. So it's not so easy to actually control the system and everything that belongs to it. So that's basically the hard thing. And also, of course, it's hard to implement these gates to actually do what you want and nothing else, for the same reason, because gates per definition are a kind of interaction, and interactions are always hard to control. So again, we need error correction, and that means we need even more qubits, because error correction basically means instead of taking one qubit to represent the information that you want to have, you take several qubits to represent the same information. So that's always the principle of error corrections. Which brings us to our next problem, and that's scalability, because most labs that produce really nice qubits don't produce very many, and the ones that produce many qubits don't produce very nice ones. Or that's my experience. So it's still hard, and there are quite a lot of people working on that, and I think there's also huge progress so far. But yeah, I'm a theorist. I'm happy when I have a few hundred qubits to work with, and so far nobody can get me that. So I'm just sitting in my lab. Now, the hard to implement is also qubit coupling. Especially 2-qubit coupling is still possible, but the more qubits you want to couple, the harder it gets. So the good news is that principally you can break down every quantum algorithm to single qubit gates and I think a CNOT gate. But then again, you need a lot of gates, a lot of qubits, so there's that again.
Why would you want to couple qubits?
To get something nice, to get a result for some calculation. Usually you need some form of interaction. Yeah, I think it will become clearer when I get to the end of my talks, where there's really an explicit system there with couplings and everything. Okay? Okay. So, yeah. So I said I would tell you something more about these 2 points of simulating quantum systems and these combinatorial optimization problems. So at this point, I should probably tell you what combinatorial optimization problems are. Who knows? Oh, okay, that's even more. So, great. So, basically, you want to find an optimal object from a set of objects. And usually that just means you have a process where costs arise, and you need to know how to optimally perform this process to save money. So it's quite common, these kind of problems. Examples are KSAT, trailing salesman, integer linear programming. And these examples, at least for big enough K, are all NP complete. So the nice thing is that all interesting problems you can map on them, principally. And what's even nicer about this, well, most. Sorry? Yeah, but I think I'll be glad if I can solve NP, and I'm happy that the other thing is for the next generation.
Could you shortly explain NP and P complete? So we're looking for just shortly in a few words.
Okay, there are really, so I mean, basically NP means non-polynomial, I think, so they're not solvable in polynomial time, probably, probably. So far nobody knows how. And complete just means, no, actually for NP hard, but actually these problems probably I just missed it here on the slide. There are NP hards, and there's a polynomial mapping from one problem to another.
harmless problem there.
So if you find a solution to one of those, everybody's really happy with you and you earn a lot of money. So, and the interesting thing for us, or for me as a physicist, is they're also very closely related to Ising spin glasses. And Ising spin glasses is a nice model, a nice physical system that looks like this. So that's my Hamiltonian, a formula. And what it describes is just a bunch of spins, here represented by these arrows, that can point either up or down. And between those spins is some form of coupling. That means that if they're aligned or anti-aligned, depending on the sign of these couplings, it's harder, it costs a lot of energy or not. So the goal is to find an optimal spin configuration, and the case is easy if all these JIJs have the same sign, for example. That's how magnetism can be modeled, among other things. And it becomes more interesting if these JIJs can be anything. And the thing is, if you want to just try out, that's a lot of configurations we have to try out. So we need a better way to actually find this optimal configuration. And as I said, it's a physical system. So also for non-physicists, if you want to have the ground state of a system, what do you do with it? So the state with the lowest energy. Yeah, exactly. You just put it in the fridge. Everybody's tired in winter, so system becomes lazy, doesn't spend a lot of energy. No, you cool it down. That's very straightforward. So that's a process that you can call classical annealing. That just basically means you take your system, you put it in a fridge. Okay, and ideally, all these little atoms, they hop, they move, and if you cool down the system slowly enough, they will have time to hop over energy barriers. So you have your energy landscape, and they can find this optimal configuration. In reality, of course, well, you're probably not very patient, so you end up in some local minima here rather than in a global minima down there. And once you're down here, you just may not get over this thing again, and you get stuck. So I drew this picture very suggestively to motivate that, but maybe we can use something else. Maybe we can, as good Swiss people, just make a tunnel here. Okay, so that's quantum tunneling, and that's what we call quantum annealing, basically. It's basically the same thing, just you want to use quantum effects now. So instead of decreasing the temperature, you apply, for example, a transverse field. It doesn't need to be exactly this way. It can also be something different, but it works quite well with that. And then you slowly turn down the field. So instead of turning down the temperature, you turn down the field. You keep it at a low temperature, and the nice thing about this is that it will actually work fine. So for all mathematics-loving people, here the mathematical expression of what I just said, it works. Just basically means it. What this whole thing says is essentially that if you have a system, you start out in the ground state of a certain Hamiltonian, and you change that Hamiltonian slowly enough, then the system, the state of the system will follow, so to speak. It will always stay in the ground state of the current Hamiltonian. And then you can still show that a bit more generally for projectors. And that's what we use with this quantum annealing. So that's great. Now we have another form of actually computing using quantum effects. It's not the same as this gate model thing. It's adiabatic quantum computing, but it does principally what we want. It computes a solution to a problem. It takes some input, it does something with it, and it gives some output in that sense. Okay? But don't mix them up. If you implement this quantum computing things, you just cannot implement the Grover's algorithm on it. It's just not the same thing. It doesn't work the same way. But then the great thing is that Actually, you can model this process classically, and there are also some theoretical results that suggest that using quantum effects may be better than using classical effects. So probably it's a good idea to actually build such a quantum annealer. So maybe that's our quantum computer of the future. And here more good news. This quantum annealer more or less already exists, or at least that's basically what they announced. Okay, so probably quite a few of you have heard of the company D-Wave. So these D-Wave devices implement just that, or are supposed to implement quantum annealing. They don't implement this gate model stuff, but they implement this changing your system gradually to get the configuration that you want. For that they use flux qubits, and they have some coupling between the flux qubits that they can change to adapt to various problems. So principally you should be able to solve a lot of problems on these devices. Again, there are of course practical aspects that not every problem can be mapped reasonably onto the architecture of these things. But still, it's quantum computer, and even the better news is you can have it, as they say. Okay. Now, as a matter of fact, there was some theoretical work, and also in my particular group, there was work done about a year ago, where they actually tested this D-Wave device, and they found that we don't actually see it work better than the classical method of just putting something in a fridge, basically, than our classical algorithms on the computer there. And that may be because it's not the suitable kind of problem, or it may be that the kind of problem that would actually profit from quantum effects cannot be suitably implemented on that device. So if that was the case, or I think anyway, it would be good. It probably, in my opinion, that's not very qualified. Probably you need to adapt the architecture a bit, and actually, you know, it's work in progress. It would be very impressive if they got it right the first time. So I think things will get better over time, and a good tool to actually get towards something that works good is if you can actually simulate these things on a classical computer, because building them is just really expensive. So there's an algorithm, there's the simulated quantum annealing algorithm. It's not clear whether it accurately represents what a quantum system would be doing. So that was my work to kind of show when it does and when it doesn't, at least for a certain class of problems. But yeah, just simulating quantum system by unitary revolution is not an option. You cannot simulate anything big with that. So you basically need to use Monte Carlo simulations. For those. Yeah, probably most know. So it's the best we have. It's something to work with right now, and to hopefully maybe improve these adiabatic quantum computing devices, so that maybe someday, or maybe at some point, the gate model variant will beat this. Right now, that's a start, and something probably worth working on. The media is quite divided about these things. I think everybody either loves it or hates it. I'm staying in between. Okay, so as a conclusion, I would probably say that with the whole quantum computing thing, we're probably still rather on this side of a computer than on our laptop side of the computer, because what we have right now that we can actually do more on than proof of concept is something that is rather specialized and does not just implement anything, and is not something with a keyboard and a display, and but something to work with.
I think in the beginning there was something about parallelizing the on a computing probably. So does it work the same way as in classical computing? Like maybe like vectorization or something like that?
Well, no, it does not really work. Well, I mean, your quantum state, you can see them as vectors, but it's not really the same, and also you don't have the same possibility to scale, to just have more. So parallelization is really taking advantage of these quantum effects that you need to cut. When you parallelize your code, you're still calling your functions several times. You're just calling them simultaneously. And this quantum parallelism that everybody is talking about is really supposed to call the function just once and evaluate everything you need to know.
The simulation of these quantum parallel systems, does it work well enough to try out how much, like, if the results are actually correct using those things?
Well, you need to be more specific on where you want to try out, and
I mean, maybe like just some simple examples, just to make sure that the quantum parallelism is actually working or it's doing what it's supposed to do.
so there are examples of people who have factorized integers. It's very small integers. You would be much faster by hand, but again, this proof of concept exists. It can be done. But it's just not at the level where it's actually useful yet. Yes?
With all the groups who are working on this, are most of them working on the theoretical concepts and proving mathematical things, or are more of them actually working on implementing this?
Hard to judge. I think it's pretty even, probably. I mean, I know a lot of experimental physicists, but partially also because some topics as state preparation or precision measurements are, of course, also have applications in other fields. They're not just for this quantum computing. So they work on that, and if they actually find something, it has some applications in various fields. Yes?
So in your last slide, you stated that quantum computing is still more in the archaic stage of things as far as the computer is concerned, right? So why exactly?
Yeah, I always got to be careful with that.
Fair enough. But why exactly is that so? I mean, is the limitation simply a hardware issue, or has the math still not been worked out? Or what exactly are we focusing on in terms of making it more viable?
Okay, so what I just wanted to say with that is that, I mean, principally on this adiabatic quantum computing stuff, you could also solve any problem in principle. Again, that does not mean it makes sense to do so. But in that sense, this gate model, if you could actually build what this gate model describes, that would be great, it would be amazing, and it would probably be what we're basically doing now with our computer, pretty close. I mean, there you actually have informatics with this gate model directly implementable on your device. It's possible to implement such a circuit on hardware, but it's just very small hardware currently, not many qubits, and not many couplings, or not very complex couplings between qubits. Yeah?
When you talked in the end about the simulation of a quantum computer by a classical computer, I thought I remembered that every quantum computer can be simulated in exponential time by a classical computer.
Yeah, exponential time is the problem.
But
Don't try it. Yeah.
The exponential time, that's the thing. And that's
Yeah.
the idea, to use the quantum device to get the exponential speed up.
Yeah, sure, but you said that with some method that you are working on, you can achieve something.
Yeah, but that's, I mean, at the end the method is deterministic. It's classic point. It can simulate certain aspects, but it cannot simulate everything. And the fact that it matches that well with this quantum annealing device of D-Wave may also be partly because this device has a lot of noise. It doesn't have very long coherence times. So certain effects, certain quantum effects may be more pronounced if you have a better device just. So it's open whether this classical algorithm can actually represent what's going on in a quantum system, but it's just currently the best tool, I think. Maybe there are some other tools I don't know about. Yeah?
So a question that's a bit broader. Given some time, will we have quantum computers on our desks or in our pockets?
No,
or
if we
will
have
stay
quantum
something for specialized systems?
I think if we have quantum computer, it will probably be rather a server farm or something at 0 Kelvin or maybe something like that. No, but I mean, what you do daily is you access servers all around the world. So I don't see any practical limitations if you have to keep a certain environment to make things work. But not at home in the sense that, yeah, I don't think it will stand on your desk at home. Yeah.
How do you see the role of ETH? It's seen globally in this field.
You're asking a lot. I've been at ETH from the beginning of my studies. I don't even know our other schools. ETH is great. I've always been here. No, I mean, there are really good people here. As far as quantum computing goes, of course, there's also a huge interest from the side of industry. Now you can ask yourself whether that's better or worse for the research that's done there. I think it's good. A good thing about ETH is I think that connections are really well, and it certainly helps for the group actually working on that to exchange what they are doing.
So let's assume we get to the point where we have nice quantum computers. What's your prediction regarding energy consumption?
Yeah, that doesn't look too good. Okay, so to be fair, I don't think it's gonna be more at the end than what our classical computers use. But I mean, part of the problem right now is, so part with Moore's law that we had so far is that for one thing we are getting closer and closer to this atomic level, things getting smaller and smaller, and the other thing is cooling. That just cooling your computer is actually a limiting factor, and that's also a kind of an emerging topic, whether quantum thermodynamics could provide some algorithms maybe or means to efficiently cool something. Yeah.
Is there something like in a computer that's, so an ordinary computer has mostly is based on the NAND operation or something like that. Does a quantum computer have more operators at its disposal to have this exponential speed up? How should I?
So I mean, there's a universal set of gates for quantum computer as well, and I mean your computer uses more than a NAND gate, but it could just use the NAND gates, and the same goes for quantum computing. It's possible to just have a certain set of gates. That doesn't mean you just use them. One thing I forgot to mention is that there's also a certain interest in, I mentioned that there's always a lot of noise and error correction is important. So there's a certain interest in topological quantum computing, that you could perform operations in a way that these are topologically protected against noise, so to speak. These are, for example, there are Majoranas, but if I remember correctly, you need, there, for example, you need something that, like a CNOT, to actually get all possible computations. But there you may want to read again.
Sorry, so what I understand is like the quantum computing, the gates are kind of like a different electronic components in a sense. Is that what you're saying?
Well, the gates it depends on what your qubits are.
Okay.
If your qubits are light, your gates won't be implemented in the same way as if they're in a solid, for example. So principally, your qubit is just something that can change its energy, basically. If it has low energy, it's your 0 state. If it's high energy, it's your 1 state. So you need something with which you can excite states. For example, optical pumping is something you can work with. So lasers are something you can work with to implement these gates. But again, it's very easy to write them down on paper, and it's much harder to find out how to reliably implement them. Yeah?
A more fundamental question about the password cracking thing. You said that the quantum computer could crack passwords faster than traditional method, right? Or
I think I don't know enough about traditional password cracking to answer that accurately.
But if I give you an example, if my Gmail account is protected with a combination of 5 numbers from 1 to 9, and I give you the opportunity to crack it, then it's practically solved, right? I mean, there's a finite list of possible passwords, and you just shoot them one randomly at a time. Everything is equally likely. So how would you have an advantage, or would you need, and also a quantum computer on the other side? Or?
No, basically that's the thing with these oracle kind of things. You need something that answers me. If I ask, is your password these and these numbers, I need something that tells me the answer, yes it is, or no it isn't. Okay, and in the quantum way, so to speak. So I need something that implements this black box of an oracle for me.
So you get a richer answer in some sense. You not only get...
No, I can ask richer, I would say. Probably. I mean, I have the possibility to input something more complex, and it still can give me some kind of feedback. So I
very
think
practically speaking, so if the Russians have a quantum computer, my Gmail account is...
Well, again, you have to see that first of all, the chance of you having a really crappy password currently is probably a lot higher than this square factor making an actual difference in guessing your password. So it's just a quadratic speed up. And it's a quadratic speed up, yes, if you really have no other means classically tend to just try every combination. But maybe you have a cat called whatever, and then you try this cat name, so you're probably gonna get smart, classically. I think probably on the classical, that's why I said I don't know enough about classical means to get a password to answer that, because there are probably a lot better ways than just ask every combination. I think just take a longer password, it's not a big deal there. Yeah.
But couldn't you implement a smarter way into quantum computing as well? Then would get still a quadratic speed up.
And that probably depends on the way exactly how it's done, but you're welcome to join the field of theoretical physicists, so find that out. That's probably some theoretical work you could actually do to find out under which condition it can still provide a speed up and when not, for which schemes. Yeah.
Suppose you get into work and it will work one day in the future. What about security? Will that be stable or will that disappear?
What exactly? So
Encryption.
So there are good encryption algorithms around already. I think it's actually one of the more developed parts of this whole quantum computing things, the encryption parts. And plus what I actually know is that, there's some hopes, whereas actually performing these computations is still a bit of a way off, at least on a scale that makes sense. Actually secure communication could maybe even be easier to achieve. So you would have some qubits, some entangled qubits to have that allow you to communicate securely, whereas the computation stuff may take a bit longer.
You're going to find the slides and also the video online on our website. And if you come up with an idea that you think is suited for a Reatch pitch, just approach us either directly via email or on our Facebook channel. Thanks a lot for coming.